Venn diagrams and contingency tables are both trying to keep track of counting the data so we can compute probabilities of outcomes we are interested in, such as speeding tickets and cell phone use. Another way to handle this issue that is particularly useful for simple problems that have become difficult because of the conditional probability questions that result from the experiment is a tree diagram. Recall the urn problem. The experiment that called for drawing the marbles without replacement generated conditional probabilities for all draws after the first. The probability of what happened after the first draw was conditioned on what happened on the first draw. An example will help. Imagine an urn with 15 marbles, 8 red, 3 blue, and 4 white. Remember that this is probability, so we know everything. How many marbles and what color? Everything. The experiment calls for 3 draws without replacement. We are interested in the probability of getting 3 marbles of the same color, any color, but it has to be the same color. This could be written as probability of red 1 and red 2 and red 3, or probability of B1 and B2 and B3, or probability of W1 and W2 and W3, where R1 is red marble on draw number 1, R2 is red marble on draw number 2, etc. for all 3 colors. On the first draw, we could get any one of the 3 colors. But to complete the required result, we have to get the same color on the next 2 draws. The probability of red on the first draw is 8 divided by 15. If we draw red on the first draw, then the probability of red on the second draw changes to 7 divided by 14. If white on the first draw, the probability of red on the second draw is now 8 divided by 14. Regardless of what draw came first, it changes the probability of all results that follow. A tree diagram is a neat way to keep track of all these conditional probabilities. The tree diagram begins with the urn that contains the marbles. We know how many of each color. This is still probability. The first branch of the tree, okay, so it's an upside down tree. Maybe you want to call it a root diagram. Anyway, so the first branches of the tree are for all possible outcomes of the first draw, either red or blue or white. On the branches, we put the probability of each event. 8/15ths for red, 3/15ths for blue, 4/15ths for white. Now, this is where the tree diagram is helpful. Whatever happens on the next draw depends upon what happened before. All probabilities from now on are conditional probabilities. So the next branches of the tree, after red on first draw, has 3 possibilities again, red, blue, or white. We put the probabilities on these branches, but remember that we are drawing from a new urn. 1 marble is gone, and it is a red marble. Following the red branch, the probability of red on second draw, given red on first draw, is 7/14ths, for blue, 3/14ths, and white, 4/14ths. The third branches, following red, can be constructed in the same way. Indeed, all the branches can be filled in with the appropriate probabilities. We now have a fully grown tree with its fruit of probabilities. To answer our question, what is the probability of getting 3 marbles of the same color in 3 draws without replacement, we simply follow the branches of the tree down the red branch, then the blue branch, and finally the white branch. Using the multiplication rule, we multiply down each branch because it is red and red and red, then blue and blue and blue, etc. The multiplication rule tells us to multiply for the word and. Then, using the addition rule, we add across the 3 colors. The formula would look like this. And here is the solution, using the tree diagram to track the conditional probabilities that are created in this experiment. It turns out the probability of drawing 3 marbles without replacement and getting all 3 the same color is 0.13.